Welcome back to the fifth and the final part of week 4 in advanced algorithms. Last time, we went over a complete example of how to build up a DP-based solution to solve the maximum weight independent set problem on graphs that have bounded tree width. In particular, we were given as input a tree decomposition whose width was at most k, so all bags had at most k plus 1 vertices in them. And the way we imagine this is that, well, the bags are kind of small, so we are allowed to brute force locally on the bags, and that's going to still be a reasonable running time. In fact, we did work out a complete algorithm where the running time was polynomial in n and exponential in k, which was exactly the goal that we were after. Now we are going to go over this exercise once more, but using a slightly modified concept of a tree decomposition called a nice tree decomposition. Last time we worked with non-redundant tree decompositions, and that was useful because we knew that the number of nodes in the tree of the tree decomposition would be bounded by the number of vertices in the graph. Here, our goal will be to modify the tree decomposition concept so that it's a little more structured and our DP solutions can take on a more predictable sort of a pathway. So that's what we are going to be talking about here. If you followed along so far, then you should be able to find the discussion in this video fairly approachable, and in fact you'll probably end up predicting a lot of what I'm going to say when it comes to building up the DP solution. So let's get started with the definition of a nice tree decomposition. So nice tree decomposition is a tree decomposition, and as before, we are going to be dealing with a rooted tree to make it convenient to give some directionality to the DP that we are going to develop. So let's say that it's rooted at a node called R, and the first thing about nice tree decompositions is the simplifying assumption that the root node, the bag associated with the root node, is empty, and the bags associated with the leaf nodes are also empty. Now, this is really just a convenience assumption and is easy to ensure, as we will see in a moment. Other than the conditions on the roots and the leaves, the rest of the tree is going to have the structure of a binary tree, which is to say that every vertex either has one child or two children, but no more. So let's look at a non-leaf, non-root vertex, something that is an internal node in the tree. And we're going to say that such nodes are one of three kinds. So the first kind of a node you can have is what's called an introduced node. So an introduced node is a node that has exactly one child, and the bag at the introduced node has exactly one new vertex compared to the bag that's associated with its child node. So if the introduced node is t and the child is t prime, then xt is basically xt prime union exactly one new vertex that does not appear in xt prime. So that's what's called an introduced node. You might say that the vertex v is introduced at the node t. Okay, all right, so the next kind of node is the opposite of an introduced node. It's called a forget node. And here what we have is the opposite of the behavior of an introduced node as well. So in an introduced node, we brought in a new vertex. In a forget node, we are going to let go of one vertex. So the vertices in a forget node are essentially the same as the vertices in the bag of its child node, except it's going to be missing one of them. So again, if t is the forget node and t prime is the child of t, then xt is xt prime minus v for some vertex v that belongs to xt prime. So that's what a forget node looks like. Notice that if your nice tree decomposition only has introduced nodes and forget nodes, then this is actually a path decomposition because every vertex has only one child, so the tree looks like a path. And in fact, such path decompositions are also called nice path decompositions, where things are getting built up slowly, one vertex at a time, as you sweep the path from left to right or from leaf to root. Okay? So what makes a tree decomposition not a path decomposition, a distinctive where you get the branching structure? You get it from the third kind of vertex, which is a join node. So the join nodes are the only nodes in the nice tree decompositions that actually have more than one child. So a joint node has two children, and the special thing about a joint node is that all these three bags are exactly identical. So xt is the same as xt1, it's the same as xt2, where t1 and t2 denote the children of t. Okay. So our claim is that if somebody gives you a tree decomposition, then you can convert it to a nice tree decomposition without increasing the width while keeping exactly the same width. And you can do this without blowing up the number of nodes too much either. So, for example, you could start with a non-redundant tree decomposition. Notice that the kinds of bags that we have described, there is already redundancy staring at us. For example, if you look at an introduced node, the child of an introduced node is certainly redundant with respect to it. Now, you might wonder, why are we doing this? Well, like I said, it turns out that it's just easier to describe DP-based solutions when you can classify all the nodes in your tree decomposition into these three simple types. So now when we do a DP, we're just going to say, well, what if the current node is a leaf? What if it's an introduced node? What if it's a forget node? What if it's a join node? And what do we have to do there? And because the transitions between the child and the parent node are so simple in each of these categories, the DP solution accordingly builds itself out usually much more easily compared to if you were doing or working with a general tree decomposition. So that's the motivation. But the price we pay for it is that we do introduce a lot of redundancy, but as it turns out, not too much. So you'll never have to increase the size of your tree decomposition by more than a factor of k, which is a polynomial overhead. So given our overall framework and goal, that is something that we can live with. Okay, so coming back to the question of how do we convert an arbitrary tree decomposition into something that is nice, well, this is something that I want to largely leave as an exercise, but let me probably suggest some hints in terms of how you might go about it. So first of all, there's a general way that you can turn any tree into a binary tree, hopefully while still preserving the properties that you care about. So for example, if you have a node which has more than two children, so let's say we have a node A with children X, Y, and Z, you could say, for example, that I'm going to keep the leftmost child as it is, and I'm going to initialize an artificial right child P, which can then take on the remaining two children Y and Z. And in the context of a tree decomposition, we also have to figure out what is the bag that we associate with this newly created vertex B. Well, that could be, for example, a copy of the bag that we have at A. So that's one way that you could reduce the degree of a vertex that has too many children. And you probably have a sense of keeping track of how many new vertices you're introducing. So you could, for example, say that, well, suppose we start with an arbitrary tree decomposition. Let's make it a non-redundant tree decomposition so that it has at most n nodes to begin with, as we already know. And then we are going to apply these manipulations to turn it into a nice tree decomposition. And if you're careful and you keep track of how many new vertices you're introducing, you should be able to argue a bound on the overall size of the newly produced nice tree decomposition. So this is about changing the structure from an arbitrary tree decomposition to something that is binary. You could also look at now the individual nodes, the nodes that have for example, exactly one child, let's say, and suppose that doesn't look like an introduced node or a forget node. For example, you might be in a situation where you have a node ABC with a child node, let's say BCD. Now, what you're going to do is again make intermediate copies of these nodes so that, for example, you go from BCD to just BC first, and then you go to ABC. That would, adding that intermediate node would make sure that this is now converted to a sequence of first a forget node and then an introduce node. And in general, if you had two bags xt and xt prime, which have some overlap and some symmetric difference, you can always tease out the symmetric difference by a sequence of forget nodes to let go of the vertices that don't appear in the parent bag, and then you can do a series of introduce nodes to slowly bring in the vertices that you do see in the parent bag. You can similarly work your way through the join nodes, and if at the end of all this the root node and the leaves are not empty, then again you can empty them out by chaining a sequence of forget nodes in the appropriate directions to obtain an empty root and empty leaves. And there you have it. That's going to be a nice 3D composition at the end of all of those manipulations. So that's the rough idea, but there are a few details that you still have to work through, so I welcome you to try doing that whenever you have a chance. Now let's actually get into the dynamic programming based solution, and we are again going to be looking at the maximum weight independent set problem. Because we have defined the problem a few times by now, I'm not going to reiterate the definition here, but you can look up any of the previous videos in this week to recall the definition of the max weight independent set problem. If you have looked at the video preceding this one, then like I said, a lot of the ideas that we develop here will feel very familiar. But nevertheless, let me try to recap the main intuition for what we are trying to do. Remember that 3D compositions have a nice separation property with respect to the bags. And if you are standing at a node T in the 3D composition, remember that we had this notation GT, which captured the entire graph induced by the union of the vertices that appear in the bags of the subtree that is rooted at T. So that was the graph GT, and the intuition we want to develop is that XT is a small window, it's sort of a border through which GT sees the rest of the world, and that's why solutions basically patch across this border in a convenient way. We only need to worry about keeping track of what is happening at the bag. So a local amount of information is enough for us to track the whole solution as we work our way up from the leaves towards the root. Let's make this intuition a little more precise with the following comment. So suppose you have some independent set which picks the vertices S from the bag XT, it picks the subset A from the rest of the graph, and it picks the subset P from inside of GT, ignoring the border XT. Right? So that's one independent set. And similarly, let's say we have another one that also happens to coincide with the first independent set on XT. So from XT, it also chooses to pick exactly S. From inside GT, this one picks Q. And from outside of GT, it picks B. So we have two independent sets. A union S union P is the first one, and B union S union Q is the other one. Now, our claim is that if, for example, the weight of the vertices in P is smaller than the weight of the vertices in Q, then the independent set A union S union P is not the max weight independent set of the graph. You can find a better independent set than A union S union P. I invite you to pause here for a second to confirm that this is clear. We are going to justify this claim in just a moment. Okay, so what we can do with the independent set A union S union P is basically replace P with Q, and our claim is that this is also an independent set and its weight is more than A union S union P. So there are two things to argue. One is that the weight is more, and the second is that this is an independent set. Well, the weight is clearly more because we removed P and we added Q, and by assumption the weight of Q is more than the weight of P, and there's nothing else that we have done. So this is definitely a heavier independent set. But is it really an independent set? All the three individual pieces are independent. A is independent, S is independent, and Q is independent. In fact, we also know that S union Q is independent because S union Q is a subset of B union S union Q. So we know that B union S union Q is an independent set. So we know that this whole part is independent. We also know that A is independent because A union S union P is independent. So in fact, we even know that A union S is independent. So the question is, Well, are there edges between A and Q? We know that there were no edges between A and P, but what about A and Q? Possibly there are edges between A and Q, but if you recall our discussions about separations, you know that xt separates gt from the rest of the world. So because of the separation property of a tree decomposition, we know that no vertex in A is adjacent to any vertex in Q. So this is a perfectly legitimate independent set, and this is basically the motivation for the definition of our subproblems. We are looking for a maximum weight independent set in the whole graph, and right now our subproblem is totally focused on the subgraph GT, and we know that GT has the small tiny window which is XT to the rest of the world, and it's enough for us to store for every subset S of XT the size of the maximum weight independent set that we can build using only S from XT, and then we can ask ourselves what's the best extension. And that's really enough because, as we have just seen, we might as well pick the best choice that we get from GT. Anything that's lesser, we don't have to worry about because of this separation property that we have. So that essentially motivates the subproblems, the information that we want to store. When we look at a maximum weight independent set, a possible solution, we don't know what it's going to pick from xt, but xt is a small set, so let's go over all the possible scenarios, everything that can possibly happen in terms of how it intersects with xt. So we can be totally exhaustive on that front, and then we try to store the weight of the maximum weight independent set that extends this choice, that's compatible with this choice within GT. So those are going to be our subproblems. That's exactly the same as the DP that we had set up last time. It's just that this time we are going to write down our recurrence in terms of cases over the different node types of the nice tree decomposition. So once again, at a node T, dp of S stores the maximum weight of an independent set in the subgraph GT, and under the constraint that when we look at this independent set S star, its intersection with xt is exactly S. That is the constraint, and these are our subproblems. This is basically the semantics of our DP table. So we are going to get to the recurrence in just a moment, but let's validate that we do get the final answer from this DP table. So as you can imagine, the root vertex leads us to the final answer, so we can just look up the value of the empty set at the root vertex. Notice that that's the only vertex subset that we actually have at the root. The root is the empty set, and this by definition basically gives us the maximum weight independent set, the weight of the maximum weight independent set in the entire graph G. So we have the final answer if we have all the subproblems, so that motivates us to solve the subproblems. Now the way we are going to solve the subproblems is to say, well, let's figure out what is dp of S at a node T. We are going to do a case analysis on whether T is a leaf node, an introduced node, a forget node, or a join node. In each case, we will write up the recurrence, and I will make the claim about the recurrence without a proof. I'm going to leave the formal proofs as an exercise. The formal proofs have been explained in the textbook Parameterized Algorithms, from where this notation and presentation is basically borrowed, and there will be a link to the reference that you can go and look up. However, I think it's a really nice exercise to try and work through the proofs of correctness on your own, since we have done it in a reasonable amount of detail just in the previous video when working with a general tree decomposition. It's a proof in a very similar spirit, except it's actually going to be simpler because there are fewer things to worry about. The scope is a lot more narrow. So I would really encourage you to try this on your own first, but you can also look up the details in the reference that has been provided. So with that said, let's get started with developing the recurrence. So our first scenario is that we are dealing with a leaf node. This is our base case, and because our leaf nodes are actually empty, there is nothing to be done here. So the empty set gets a value of 0. There are no children. There's nothing else to do really. So those are some really easy base cases to get out of the way. Now let's look at an introduced node. So suppose we have the node T, which is an introduced node. The bag is xt and the vertex being introduced is v. And suppose the child node is t prime. So we know that xt is exactly the same as xt prime, except that it has this one extra vertex v. So one thing we can get out of the way right in the beginning is to say that if S is not independent, then this dp value is not well defined. So we are going to denote that with a minus infinity, just as we did before. Now, there are two natural cases that come up when we are looking at a subset of xt that we may want to distinguish between. The first case is when you have a subset which does not involve the vertex v at all. And on the other hand, you might have a subset which does contain the vertex v. Now, we treat these differently because in one case, notice that, well, you're thinking about the best independent set that you can get in GT that intersects xt at exactly S, and S doesn't even contain V. So this newly introduced vertex is really not playing a role. In fact, it's forbidden from being chosen. So we could now right away copy over a dp value from the child table. If you like, you can pause the video for a moment here to think about what this should be. Alright, so what we can do if v doesn't belong to S is simply set dpt of S to dpt prime of S. And the intuition for that is that in gt prime, right, we are looking for the max weight independent set that overlaps with xt prime at exactly S. Notice that xt prime and xt are pretty much the same bags except for the vertex v. So we really can just bring this value over. Previously, we had to go over all possible subsets y, which respected the S constraint from the parent node. But now the point is that the parent node is practically the same as the child node. So the S constraint carries over quite literally. So we don't have anything else to worry about. We can just use this value directly. On the other hand, if V does belong to S, then, well, we're going to be doing something very similar, except that now the weight of the vertex V does contribute to the solution, so we have to remember to add it. Once again, feel free to pause here for a moment and try to come up with a recurrence yourself before moving on. Alright, so one thing that you might worry about is what if V has an edge to some vertex in the set. Notice that that's already been accounted for over here, so we are assuming that we're dealing with an independent set. So we add the weight of the vertex V, and now from T prime we basically pick up the value for the rest of the set, which is S minus V. That's a set that we are going to find in the DP table below, because that's a subset of xt minus v, but then xt minus v is exactly xt prime. So we are going to find that value waiting for us, and we can just pull it up. Once again, you can formally prove the correctness of this recurrence that's being claimed here, but that's something that I'm not going to be getting into, and I would say that it's a good exercise to try and figure out yourself or read up from the reference. Okay, let's move on to the forget node. In the forget node, we have an opposite situation. Xt excludes exactly one vertex from xt prime, and once again, if the set S under consideration is not independent, the dp value is not well defined. But what's more interesting is what happens when S is an independent set. So remember, in the previous DP, we would look at all subsets Y of the child node such that Y respected the S constraint from the parent node, right? So we looked at xt intersection xt prime, if you remember, but now xt intersection xt prime is basically this whole set right here, except for the vertex V. So we know that in this region, which is xt prime, other than the vertex V, we basically have no choice but to exactly pick the set S that has been fixed above. That's going to be exactly the same. However, when it comes to V, we have a choice. Okay, so we could either pick V or we may not, and there are going to be exactly two DP table entries that reflect these two choices. Again, if you like, pause here for a moment to try and figure out this recurrence yourself. Okay, so the two DP tables of interest that are consistent with the choice that is being demanded at the parent would be either the set S itself, where we don't pick V, or the set with V included, so S union V. Those are the two DP table entries that are of interest, and we simply pick the better of the two. That is how you bid farewell to a vertex V. By the way, notice that in a nice 3D composition, a vertex V is forgotten at exactly one node, although it may be introduced at several nodes. Imagine how the vertex coherence property works. So if you imagine vertex coherence on a nice 3D composition, you're going to see that the subtree that's formed by all the bags that contain a particular vertex V is going to have exactly one vertex that is closest to the root. So that vertex is going to be the vertex at which that's when we see this vertex V last. So its parent is going to be the forget node. But on the other hand, all the leaves of this subtree are places where this vertex gets introduced. So a vertex can be introduced multiple times, but it gets forgotten only once. That's a nice thing to know about nice 3D compositions. Okay, so we have one case left in the recurrence, and that is a join node. A join node is very conveniently, it's three bags that have exactly the same vertex set. So once again, there's this formality that if S is not independent, then the DP value is not defined. But otherwise, notice that whatever set you have at the parent node T, you're going to find the exact same set in both the child nodes. And since we are required to carry over this constraint as we go into the child nodes, and the child nodes are exactly the same as the parent nodes. We just have to ping those DP table values. But there's a small adjustment that we have to make as we try to combine these DP table values. Again, the combination will be by taking a sum, as we did in the previous video where we had multiple children. In fact, so we were doing a sum over all children. Now we just have two children, so we are going to be combining by a sum. But is there some adjustment that we possibly need to make? Think about that for a second and come back when you're ready. Okay, so what we are going to do here is simply take the DP values for S at T1 and T2, and those are going to give us two independent sets, and we simply take the union as we merge these two graphs. So as we think about the graph that is GT1 union GT2. But really, these are two graphs that meet at the bag XT, and we are trying to combine two max weight independent sets from both sides. And these two maximum weight independent sets, by definition, by the semantics of the DP table, both of them have the vertex S, have the vertices of S sitting in them. So if we simply add the weights of these two independent sets, then we will end up overcounting the weights of all the vertices in S. So to adjust for this overcounting, we have to subtract the weight of S. This is similar to what we were doing before. Now you might wonder, why don't we do this adjustment when we are dealing with the introduce node and the forget node? I would encourage you to think about that. Notice that the point here is that we are only going across one child, and we are not adding the weight of S separately. So it's just folded into the DP table value. We are not combining across multiple children, and we are not adding W of S again. So that's the reason why an adjustment is not needed here. We are not overcounting anything if you look carefully into the recurrences for the introduce node and the forget node. But you can verify that on your own time, and hopefully you're convinced that all of these recurrences intuitively at least make sense. And once again, let me just emphasize that you can absolutely sit down and write down formal proofs for all of these equalities, and that's a really nice thing to do based on what you have learned about how to make these arguments when we made them for general 3D compositions. Okay, so that's the entire recurrence and we're basically done. Hopefully you can see why doing DP over nice 3D compositions is overall more pleasant than doing it over general 3D compositions. The only price that we pay here is the fact that we're dealing with more nodes in the tree of the 3D composition. But in terms of simplicity of presentation and in terms of just the fewer cases that we have to deal with, I would say that a nice 3D composition is almost always usually the nicer thing to work with. One last thing that we want to figure out is the running time of our approach here. So notice that at every node of the 3D composition, we are going over 2 to the k subsets. But now we are not summing across multiple children and we are not going over all possible subsets of the child bags. Notice that in all cases, all that we are doing is combining a constant number of entries after some polynomial time sanity checks. So our running time per bag is 2 to the k times some poly k, and the total number of bags, because we're dealing with a nice 3D composition, it's not at most n anymore, but it's n times k, but that k gets absorbed in the poly k again. So we not only had a more pleasant set of cases to deal with, we also have now an improved running time compared to the 4 to the k that we had before. So that's it with nice 3D compositions, and we've solved maximum independent set now multiple times, actually maximum weight independent set multiple times, first on trees, then on thin grids, and then, well, on path decompositions, although that was left as an exercise, then on general 3D compositions, and now finally on nice 3D compositions. So I hope that by now the maximum weight independent set feels like a problem that's very familiar and that you understand well. So we are going to explore this a little bit more in the assignment, and in the practice assignment, you'll have an opportunity to try solving a different problem over bounded width 3D compositions. I also promised you at the beginning of this week that I will tell you about how to compute optimal 3D compositions, at least approximately, but that's something that I am going to follow up on when we come back and talk about approximation algorithms in a future week, instead of trying to cram it all in here. I realized after recording all of these videos that there was already quite a bit to absorb here, so we don't have to worry about computing optimal 3D compositions just as yet. That's something that we will return to in a future week of this course. But in the meantime, I hope you have fun thinking about generalized trees and working with DP-based solutions for your favorite problems on these structures. I'll see you around next week when we come back and talk about flows.